Good afternoon, everybody. How are you all doing? My name is Sridhar Rajagopal, and today I'm going to give a quick introduction of how you can incorporate AI in your next Maker project. So how many of you have already worked with AI? Awesome. So you can help me answer questions then. So how many of you have used AI in your microcontrollers? How many of you have used AI in your microcontrollers? Okay, awesome. So what is AI? Currently there's a lot of buzz around things like ChatGPT, large language models, generative AI, and that is a subset of a broader class of problems called deep learning, which itself is part of machine learning, which uses data sets to train machines to be able to classify and predict problems. And artificial intelligence, so this is itself a part of artificial intelligence, which is a broad branch of computer science that aims to create intelligent agents that can learn to reason, learn, and act autonomously. Right, so what is machine learning? Machine learning is basically utilizing data sets to learn patterns and make predictions. And there are certain different classes of problems that can be solved, like classification, wherein you are presenting a set of data and you're learning to classify it into different buckets, or regression, which is trying to map the data into a line or a into a straight line or a curved line. And clustering, in which you're trying to figure out patterns in the data. And dimensionality reduction is where you take data and you're trying to figure out which are the features of it that are the most important. Machine learning itself can be classified into supervised learning, wherein you take labeled data sets and use those to train the machine to be able to make classifications and recommendations. And some examples are neural networks, support vector machines, and regression. Then unsupervised learning, algorithms like clustering and anomaly detection utilize the data but don't require any kind of supervision, and they try to figure out structure in the data themselves. And reinforcement learning is the example wherein something learns by trial and error, such as playing a game until it gets it right and improving along the way. So in all of these, we are mainly interested in deep learning. That is the thing that has really revolutionized AI of late. And it has been something that has been computationally intensive and able to do it in the cloud with lots of compute resources. And there are a couple of things that have changed along the way to allow for it to be utilized on things like your microcontroller, and that's what Edge AI is. What is Edge AI is it's bringing AI and machine learning algorithms closer to where the data is being generated. And there are a couple of things that have happened that have facilitated this. One is the microcontrollers themselves getting more powerful and more capable, going from 8-bit to ARM processors. And the other is the software frameworks, where your machine learning models have optimizations that allow for it to have a fully trained model that can run inferences that is small enough to run on your microcontroller. So what are the advantages of, before that, let's see a little bit about adoption of Edge AI. You have smart cars and autonomous vehicles. Everybody knows about those. Wherein it's using the data that is generated, it's doing analysis on it, and it's able to react to it quickly. And then you have security and surveillance systems with face detection. In industrial IoT, you can have anomaly detection and predictive maintenance. In healthcare, you can have fitness, sleep tracking. And in retail, you can learn to check for inventory and customer reactions and so on. So what are the advantages of Edge AI? That's can be described with an acronym, BLURP, which is bandwidth, latency, economics, reliability, and privacy. With bandwidth, one of the advantages of running machine learning on the device is you don't have to transfer all of the data to the cloud. So that reduced bandwidth allows for greater economics. So you have lower costs and also enhanced security and data protection because you're not sending a whole ton of data to the cloud. And this also results in reduced latency. Because of this, you are now capable of taking real-time action. So this is useful in things like autonomous vehicles, right? So you don't want to wait for a network connection to send it and get a response back and things like that. And here are a few popular use cases of edge AI. In image and video, you have things like image classification, object detection, pose detection, and facial recognition. And here is an example of using edge AI.
Have you ever noticed cameras like this at an intersection near you? You may believe those cameras are to catch you running red lights and to send you a ticket in the mail. Let's open up this traffic signal controller cabinet here, and let me show you what they actually do. As you can see, these cameras are actually used for vehicle detection. As these vehicles pull up to the stop bar, these cameras will lock in a call for them to get the green light. You see that this car out here is getting detected by these cameras, and they are sitting on top of phase 4. And as you can see, a call is held in on phase 4, and they will be getting the light next. These cameras even have a radar attached to them, and as you can see, this is showing an alt sensor, which is that radar, and is picking up advanced vehicle detection. See, these cameras are designed to make this intersection more efficient, which means you'll spend less time at red lights and more time moving on your daily commute. The world of traffic signals is unique and fascinating. Make sure to hit that follow.
So thank you, Traffic Doctor, for that fascinating explanation. With audio, you can do stuff like sound detection, like glass breaking or faucets running, or if the motor is running properly or not. You can do audio classification of trying to figure out what is the bird that you're trying to identify, or detecting coughs and sneezes, voice commands, and keyword detection. And there are a bunch of other interesting examples with time series data from sensors that can use like for temperature and humidity with smart thermostats. You can use current for anomaly detection, and then accelerometers and gyroscopes for sleep and fitness training and fall detection, and then environmental sensors. And now we can do a lot of gesture recognition too. So, the stuff in Minority Report is no longer just fiction. Now, how do you go about getting started with Edge AI? The first step is, you want to figure out what the platforms are. So the two most popular ones are TensorFlow Lite. TensorFlow Lite is also called as Lite RT now. And it allows for optimized models that can run on microcontrollers, so that's like awesome. And it can also, it has a lot of pre-trained models and a lot of examples, and it is open source. PyTorch Mobile is another open source platform that allows for models to be run on mobile devices like iPhones and Android. It's no longer being actively supported, and it has been supplanted by something called Executorch. And there is word out there that can also create models that can run on microcontrollers. So I'm looking forward to that. There are other platforms, like, for example, STM has its free AI model optimizer that you can take existing models and then convert them to run on STM32. And there are other ones like OpenVINO, NVIDIA Jetson, and Caffe2, but these are for more traditional machine learning, that's not aimed for devices. Then you have a platform called Edge Impulse. I'm sure most of you are familiar with it. Edge Impulse is really nice because it offers support for a whole bunch of different hardware and also software platforms, and offers a lot of tools for data collection and data cleanup, and also creating your models. So that would be a great way for a newcomer to get started, or also if you don't want to spend a lot of time and want to do things quickly. So first thing you want to do is figure out your hardware, and some of the hardware considerations are, of course, what is the hardware that you are familiar with, and also the platform that you are familiar with. But also, how much processing power that it has to be able to run the models that you're interested in. You can, starting all the way from low-end microcontrollers to CPUs and GPUs and NPUs. And differing hardware have different capabilities. So for example, a low-end MCU might still be able to do stuff like audio classification and time series data analysis. So if that's all you're doing, so that would be a great way to get started. But remember, when you're choosing a hardware, to also account for resources for the other stuff that you'd like to do other than machine learning, and make sure that it has enough resources for that. So all of this, there's a whole bunch of different possibilities out there, and it's a dizzying array. So how do you pick something, right? So there are a few tools that you can use to help you narrow down your choices. So for example, if you go to TensorFlow Lite or Lite-RT, they have a list of supported hardware, and you can see some of the usual suspects here, like Arduino, SparkFun, Adafruit, etc. And then if you go to Edge Impulse, that also publishes a list of supported hardware, and their list is quite extensive. Again, a whole bunch of Arduinos that we see here, with microcontrollers plus accelerators. So these accelerators help the machine learning models to run a little faster and give better performance. And also CPUs, you can see that Raspberry Pi 4 and 5 are both supported, and also GPUs. And Google has a neural processing unit called TPU. They call it Tensor Processing Unit, called Coral. And the interesting thing is they're coming up with a new development board that integrates a TPU with a microcontroller, and this is still in the pre-order stage, so if you're interested, please make a note of that. Definitely looks interesting to me. And some of the other hardware considerations are you want to make sure that you have enough resources, and you want to be able to run other workload on it that you're planning for. And it'll be useful to have stuff like Wi-Fi or Bluetooth or cellular to be able to interact with other devices and cloud-based platforms for a kind of a hybrid solution. So what are the steps to go about getting the edge AI working on your microcontroller, right? So it starts with data collection, then you prepare the data for training, you choose an appropriate training model, then you go about training and optimizing the model, test it, evaluate it, and then finally deploy it. And some of these are done in an iterative fashion as you kind of evaluate the accuracy of the model and figure out that you might need more data and so on. So while it's fairly straightforward and swift to create a demonstration model, it is not an easy task to create a model that will work well in the real world, and that can require a significant time and effort. This revolves around data collection, data preparation, the compute resources that you'd need for training a model, and then crafting the models to operate effectively on your resource-constrained devices. So you'll have to make trade-offs between processing power, the classification accuracy, and energy consumption. So the first step towards this is you're going to need a lot of data. So you're going to collect data. So how do you go about doing that? You can use data that is coming from your own sensor, and you can search for, there are a lot of public data sets that are out there, and so you can go and search for them and see if they are appropriate for you. You can gather data from public sources. And there are also other techniques like data generation, wherein you're generating synthetic data to augment your real-world one. And you can also use data augmentation techniques that stretch out your existing data. So if you have, for example, if you have a bunch of images, you can flip some of those images and rotate them, et cetera, to create more samples. Or with audio, you can pitch shift your audio. Here are a bunch of AI training data sets. that are available. I kind of pick these up from the internet, and so you can, make a note of these. These would be useful for you, and you can also go and search and find your own data sets. So once you have collected your data, you'd want to prepare it. You'd want to clean up the data. For example, with images, you'd want to normalize the image size. For audio, you'd want to normalize the audio length. And then you're going to go about labeling the data. So the labels are what are going to help train the model, so this is a really important step. And once you have the labeled collected data, you can go about training. So the quality of the how good a model is really dependent on the quality of the input data. So data is important, so please pay a lot of attention to it. And there are many places in which bias can creep in when selecting training data. So selection bias is where you don't have enough data available to truly represent your problem space, and so the machine learning model does not fully represent the solution. With recall bias, it revolves around the data labeling process, in which there can be subjectivity towards applying labels. So, for example, if you're trying to classify something as partially damaged or damaged, the notion, so somebody could label something as partially damaged while another person could label it as damaged, and so that results in recall bias. Exclusion bias is when you decide that some features are not important and you throw out that data because it might be an outlier. And once you train it, you find that that feature gets underrepresented in a real-world example. And with association bias, what you're doing is, if your training data has a certain type of data that adds an association in. For example, if your data is that all pilots are males or all flight attendants are females, then that's what the model is going to know about, and it's not going to know about female pilots or male flight attendants. So that is an association bias. So these are some of the things that I'd like you to keep in mind when you're figuring out your own ML project and how to go about collecting data. So once you've collected your data, one of the things that you would need to do is feature extraction. So you might need to transform the data before it is actually fed into the neural network. So for example, with audio, we typically use a convolutional neural network for classification, which is similar to what is used for image classification. So what we do is the audio is converted into a visual representation, like a spectrogram, and then it's fed into the neural network. And then you have the model selection. You'd want to select a suitable class of ML model for your task at hand. And here is where tools like Edge Impulse can really help, because they have a bunch of pre-existing models that are available for use. And they also have an advanced mode in which you can go in and actually look at the code and change the code and tweak it around and do things. And then once you have your model, you're going to train it. So during the training stage, you're splitting the data into training, validation, and test sets. Typically, about 60 to 80% is used as training data, 10 to 20% is used for validation, and another 10 to 20% for testing. So the test data is something that you don't use during the training phase. It's something that is new. So once the training has been done, you use the test data to verify it. So then you can test the model with data that it has never seen before. So this training is done iteratively over several epochs. And as the training happens, the weights and the activations get updated, and the model kind of improves gradually over time. And the validation set is used to make sure that the training is progressing along the right path and you're not overfitting the data. And now we talked about data and training and models. So how do you go about training it, right? So this is where it's going to require a lot of resources and can take a while. So while you can have deep learning models that can run on a microcontroller, that's the final trained model. So the training itself, it cannot be done on the microcontroller, so you need a lot of computing resources for that. It's something that happens over a long period of time. So you can use your own computer for it, but know that it's going to take up a lot of the resources, and it's going to tie up your computer. And you could try to then utilize the GPU on your computer, but then know that this kind of DIY work comes with its own cost of time and effort. There is another, so this, when you're using the resources, GPUs, this is where GPUs shine. They allow your training to happen faster. So if you have some GPU, you can utilize that as well. Now, there is Google has a site called Colab, and that allows you to run your training models on it. And so this offers some computing resources, including the GPU that you can use. However, just like any free resource, it's resource constrained, and it comes with restrictions. So if you have a lot of data and a lot of training to do, this is something that's going to be cumbersome. Edge Impulse also offers computing resources, and additionally, it does a lot of the heavy lifting with different stages of the AI development, like data collection and viewing the data and training and tweaking it and so on. So once you have trained your model, you'd want to test for accuracy. This is where the test data set comes into play. So the test data set is data that the model has never seen before. So based on the results of this, you need to iterate. You might need to go and collect more data. You might need to clean up your data or verify that the data is labeled correctly, tweak the model, and so on. And then once you are satisfied with how the model is performing, you have to deploy it on your hardware. So how do you go about doing that? You can do that as purpose-built binaries for your hardware, and there are tools like Edge Impulse that will compile your model into the suitable binary for the hardware that it supports. So you can just like drag and drop it in, and it works. Everything is great. Or you can download it as a C++ library and integrate it into the rest of your firmware. Just make sure that the hardware that you're using has enough resources, not only for the model, but also for the other functions that you're planning to do. As you are running this on your actual hardware, you might see that you might need to do some optimization maybe because the inference is taking too long, or the feature extraction step is taking too long. So you want to kind of trade off between what is the model size, what is the performance, and what is the accuracy. So you might go about and try to do something called as quantization, which is reducing the accuracy of the weights that it's using. So the model becomes slightly less accurate, but performs better. Or you could prune the model or tweak the model. So there are a whole bunch of trade-offs that you can do. So again, Edge Impulse is not sponsoring this talk, but I would like to say that they have done a pretty good job with helping people get ML working on their devices, because they go through the entire flow of how you start from data to the actual model. There are other ways in which you can incorporate AI into your project. You can use already pre-trained models. So there are sites like Kaggle that have models that are in the TF Lite format that you can use, and then compile it into the library that you're going to deploy on your hardware. Or you can use things like transfer learning, wherein you can take an already existing trained model and repurpose it for other data. And this kind of technique allows you to save a lot of time on training and be able to get to your result faster. So, we've looked at Edge AI, and we looked at a bunch of different applications of it, like image, video, time series, and so on. And it's not as powerful as running AI in the cloud, right? But especially things like generative AI. But with the future of Edge AI, they're trying to do more generative AI at the edge. And then there are other techniques like distributed AI and federated learning and swarm learning that you can utilize towards a divide and conquer kind of approach in not having like a huge model that's running in the cloud, but like sub-models that can kind of collaborate and work together. And voice commands, gestures, and facial recognition are all examples that are getting increasingly integrated with edge AI systems. And this is something that you could totally do to your next project to make it more awesome. With generative AI at the edge, here are a couple of interesting links for you. MIT has this thing called Tiny Chat, which is a very domain-specific model for generative AI that can achieve real-time interactions on edge devices. NVIDIA also has a developer kit that's designed to deploy large language models on edge devices, and Qualcomm is also doing some work in that area. So are you ready to dive into the world of AI? If so, here are a few resources for you that I would like to leave you with. Udacity has a couple of really nice courses and that are easy to follow along and learn from, called Introduction to TensorFlow and Introduction to TensorFlow Lite. Edge Impulse also has a whole bunch of end-to-end tutorials that will help you get started and going. And PyTorch has a tutorial called Deep Learning with PyTorch. And there are also other interesting projects for inspiration that you can check on hubs like on Hackster.io and Arduino Project Hub. And ST has a bunch of interesting case studies on their website here. And if you have any questions, feel free to email me at Sridhar@protostacks.com.
Awesome, Sridhar. That was amazing. I'm writing a book on this stuff, and there was things in here that I had forgotten about, and I'm going to add to my book. So that was really great. Any questions for Sridhar? Oh, I see there's one over here.
Hi. Thank you for your presentation. You're going over sort of the new developments of like MPUs and TPUs being used on like microcontrollers like Coral or prototype boards. I'm curious if you wanted to develop something, say, whatever your project is, and you wanted to do reinforcement learning, like as it's trying to do it, would it need to be able to transmit data as it's collecting to like a stronger computer or server or the cloud to do the training and feedback, or is there any way to bridge that connection, or maybe collect data and then train it and then go back and repeatedly iterate on it?
I mean, so this is where, when I said for you to plan the resources for other stuff that you might need to do. So if you have, like, say, Wi-Fi, that definitely opens up the room for communicating with other devices and doing it in a more federated approach. So you're kind of doing a classification here. You can send the results to the cloud, and then that can take that and run with that. And so this kind of model is definitely possible.
If you saw Jay's talk earlier, he actually had an LLM and an embedded model working in unison, kind of like what you're talking about. The tricky thing with that would be is you'd have to replace the model on the microcontroller and kind of in real time. I don't know how you'd achieve that, but I like it. Any more questions? Raise your hand if you got a question. Oh, thank you.
Hi. I guess I just kind of want to think about the example you gave earlier where you were showing pictures of dogs. And you're saying, hey, we could build a CommNet here. You could grab some pictures from free sources. You can label it and train a CommNet, right? So when you say labeling, you're literally talking about, I need to go in and label every single picture that's a dog versus every single picture that's not a dog, right?
Correct.
So what's the minimum sample size to train a decent convolutional neural network doing that?
So that is a great question. It depends, right? It depends on what are you trying to achieve. Are you trying to send it to be able to identify all dogs in the world, or are you trying to identify the dogs in your neighborhood, right? So a good sample size to get started would probably be about, I would say about 1,000 to 2,000 images, and then take it from there.
One last question.
As a maker who's looking at diving into AI for my personal DIY projects, do you recommend going from a large model that feels good for the real world and then going localized. For example, if I want to do something for my house, right, and I'm never going to have stools, so I don't have to label that stools are a chair. Is it better to go with a larger model and then neck down, or is it better to train it from the data that I'll have to collect in my own house?
It's always is good to think about how general you can make your data collection to be. Spend a little bit of time and effort on that, because that time and effort that you're spending initially is going to pay off, because it's going to make your model better. Because even in your own house, like tomorrow you might go and buy a stool, but then what are you going to do if it's not going to? So if you kind of think about that in that light, and it's a trade-off between spending enormous effort in gathering every single image under the sun versus let me start with something and that is reasonably sized. I would go with that approach.
That was really fantastic. Thank you, Sridhar. Let's give him all